I will now use all the experiences from this series of nerds videos to try to make an even better selective amplifier to use as an oscillator. So first I will design the filter. What you see here is a simple filter with a diagram like this one. I have set it to present an impedance of about 250 ohms, both directions, so it is symmetric, and this is what I see on the network analyzer. And I go for the bandwidth function, and I see the Q is 74,800 or something. This is what I see at a power level of minus 20 dBm according to this instrument, which isn't quite correct, by the way. I now set the power to 0 dBm and watch the curve here. It's shifted in frequency and it's no longer symmetric. So this is too much power for this filter. I now added 3 crystals more, so there are 4 crystals in parallel. And I have retuned the trimmers to still have the same response, as you can see here. 250 ohms, and I've done that from both directions. And then marker search and bandwidth. The Q is 75,000 and the loss is 9 dB. Maybe, well, I don't know the reason why the loss is higher. I think it shouldn't be. Anyway, I can now increase power. This is at a power level of minus 10 and I go up to 0. And now 0 dBm is perfectly okay. I have added an amplifier and an attenuator to set the level 6 decibels higher. It means the loss reads now 3.5 dB approximately, while it was 9.5 before. And this is at minus 20 dBm, and I go for 0 dBm now. And if you look at this curve here, the change is very similar to what I had with 1 crystal and 6 decibels lower power level. Conclusion: crystals in parallel allows a higher signal level, higher by the number of crystals. So this directly improves the signal because the thermal noise on the crystals, well, that is going to be lower because of the lower impedance on the resonance. So that's another advantage. Also, far from resonance, the impedance is going to be lower, which means that the noise from the amplifier will be lower because the current noise is dominating. So crystals in parallel is a significant advantage. I have gone back to a single crystal, and then this is what I see on the bandwidth. And now it says 9.2 dB, so it means the first I showed with 7 dB was not carefully tuned. I may have forgotten that one side affects the other, but now it's 250 ohm in both directions. The important thing for the narrowband phase noise is not the Q, it's the derivative of the phase with respect to frequency. That's what we see here. The span is 1 kilohertz from here to here, so it's 100 Hz per division. It means the phase goes from 69 to 27 degrees over 50 Hz. That is 0.84 degrees per Hertz. I have added one more crystal like this, and that changes the filter, as you can see here. The crystals are loosely coupled, attenuation is much larger, but Q is also much larger. The phase now goes from 158 to 72 in 50 Hz. This means that the derivative of phase versus frequency is twice as large as before. But that is at the expense of a much higher loss, so I will tune it a little bit differently. I have increased the coupling capacitors now, between the crystals and also between input and output and the respective crystal. And now I see here Q is 100,000, so it's significantly higher than before. Loss is 12 dB, that is 3 dB worse than before, acceptable. And the input impedance is now 100 ohms, and I've tuned it for 100 ohms in both directions. So, and then I look at the phase derivative. So it now goes from 33 to minus 38 in 50 Hertz, or maybe minus 33 to 33 to minus 35 in 50 Hertz. The phase slope now is from 34 to minus 35 in 50 Hertz. There is still an improvement in phase derivative from 0.84 to 1.36, but it's not as big as with much higher losses through the filters. This is the two-section crystal filter at a wider frequency range. The ultimate attenuation is 70 dB, but it's much better here, there, where there is the series resonance. This is the single section filter, and you can see the attenuation is only about 40 dB, well away from the resonance. This is not enough when using a standard signal generator to investigate what happens far from the center. What I can do is to combine this filter with a series resonator, because a series resonator, then one can cancel the parasitic capacitance of the crystal and get a very good attenuation far from resonance. This is one way to make a filter using the series resonance. I set the resonance frequency with this trimmer and the impedance with this one and the one which is here. I could eliminate this one by making this capacitor bigger, but that's not so easy to adjust. So this is what I do for this experiment. The network analyzer shows this, and the bandwidth function tells me Q is 78,000, loss 7.5 dB. So it is pretty similar to before. But if I change the frequency span to 100 kilohertz, it is very different from what I had on the parallel resonator. Here is the parallel resonance, where there is nothing coming through the crystal. And here we have a fairly large level, and also here. I increased the span even more, 1 megahertz. And you can see spurious resonances, there are always some of those. So I save this display, data and memory, and save this. And now I will make a small change. An inductor in parallel with the crystal will balance the parasitic capacitance at some specific frequency. And by selecting the optimum inductor, I can get a result like this. So this is data now, and this is what I had without the inductor. And here are both of them. I don't know how well it is visible. Anyway, this is an interesting thing, so I can combine this filter with the other filter, because I want the very high impedance for the field effect transistors. But wanting two filters in series, nothing prevents me from using a series resonance for the first filter. The inductor is 27 microhenries, and I have tuned it by placing it near a magnet. I will remove the magnet while looking at the spectrum analyzer, at the network analyzer. And now the magnet is not there anymore. And you can see it is a little bit more unsymmetric. The resonance has moved here. So this is the filter I will try. Small inductors here and here to set low impedance on the two sides of the very low impedance crystal group. I prefer inductors over capacitors because I'm unsure about the losses of such big capacitors at 10 megahertz. And then the output here is the high impedance point where I will put the junction FET transistors. I am monitoring this point now through a 2PF capacitor, which is not loading this output significantly. Here is what it looks like. You can see the inductors are very small, just a couple of turns. And this is what I see on the network analyzer. Impedance is close to 50 ohms, obviously, because I have this 36 ohm resistor in series. Maybe I should make it a little bit smaller to have some mismatch. That means to get some more signal through. And you can see the shape is not perfectly Gaussian. It's a little bit flattened because of the coupled resonators. The Q is 85,000 as computed here, but more important is transmission here. On 50 kilohertz, the phase shift is 88 minus 22 degrees. This gives me 1.32 degrees per hertz. So it's a little bit better than having just a single resonator that gave me here 0.84. I have added some amplification up to the point where I can see the curve change when I change the power. So I go down to minus 20 And you can see the curve here changed just a little. So I go back to 0. So I think this is about the maximum level that the crystals can handle. So I look with the oscilloscope probe at the input connector of this filter, and then I watch the amplitude I see, and you see it changes while sweeping across. So the level I have at the resonance is about 3.6 volts. To get the same voltage from the signal generator, not even 15 dBm is enough. So for this to be reasonable, I have to design an amplifier for the output stage of this unit to deliver at least 25 dBm. So the filter is finished. In the next video I will describe what I do to add the amplifier stage. That is the first amplifier stage following this kind of high impedance point that I have created.